In this video, we will learn about the design methods and the design equations for the power stage components of a boost or a step-up converter. In particular, we will look at the equations for the various parameters for selecting the input inductor and the output filter capacitor, as well as the requirements on the power MOSFET and the diode. We learned the basic operating principles of a boost converter in a previous video on boost converter analysis, and we derived the input-output relationship for the boost as 1 over 1 minus D, which gives us the expression for the operating D under any given conditions to be 1 minus the input voltage divided by the output voltage. Now, for constant output and variable input voltage applications, we can establish the range of variation in the duty ratio as shown here. So D varies when the input is at the maximum value, that is when D is at the lowest. So from a minimum of 1 minus Bn max over the constant VO to a maximum value of D given by 1 minus the minimum input voltage over VO. So as the input voltage increases, the D decreases to regulate the output voltage at a given value. Now, in the same video, the boost converter analysis, we also looked at in detail the various current and voltage waveforms at different points in the schematic, and we will be making use of especially the waveforms for the inductor voltage and the current and the capacitor current to come up with the design equations for L and C. Let's begin with the design parameters for the input side inductor L. The voltage and current waveforms of this inductor are shown here. So VL is V in during the on interval, and it is V in minus VO during the off interval, this being a negative value. And these two magnitudes give the slope of the inductor current in the on and off intervals. Now, since the inductor is in series with the input, its average is same as the input current IN, which can also be written in terms of the output current as IO over 1 minus D using the power balance principle. The peak-to-peak variation is defined as delta IL, so that's a peak-to-peak ripple in the inductor current. Now, the suggested method for designing the L is to limit this peak-to-peak inductor current ripple, the delta IL, to some chosen value. This is similar to what we did in the design of L in a buck converter. Now, the choice of delta IL can be done in one of many ways. For example, we can choose delta IL to be about 10 to 20% of the maximum average value of the inductor current, which is same as the maximum input current IN, 10 to 20% of maximum input current. Or, since the inductor is one of the inductor current, or its ripple is one of the variables that the user sees, since the L is on the input side, very often there may be user given specifications on the maximum value of the input current ripple. In that case, that's what we should use in this design process. So delta IL would be a specification given to the designer of the boost converter. Or the delta IL may be dictated by the continuous current mode considerations. For example, if it is required that the converter operates in CCM mode down to some specified minimum load, then that dictates the choice of delta IL and therefore the choice of the inductor. Now, regardless of how we select the value for delta IL, once we have chosen a specific value for delta IL, then we can derive the expression for the required L value to meet this delta IL specification under all operating conditions. So just like how we did in a buck converter, we could either use the on interval or the off interval. Let's use the on interval for the boost converter case, and the basic equation is L di over dt is VL. So during the on interval, this di by definition is delta IL. This dt is the total duration of on interval, which is d times ts, and that is equal to the inductor voltage, which during the on interval is simply V in, as shown here. Now, since we are considering constant output voltage applications, it is probably a better idea to express the required L value in terms of this constant output VO. So Vn in a boost converter is equal to VO times 1 minus D, and so that gives us the required value of L to be VO times 1 minus D times this DTS over delta IL. Now that is the required value of L, and if you look at this expression, VO is a constant and TS 1 over the switching frequency is also a constant. Delta IL has been chosen. So the D and the 1 minus D terms, those are variable. They vary with the input voltage. Depending on the operating condition, the D can be very different. Now exactly what value of D should be substituted in this expression to determine L, that is something that we will discuss in the next slide. But before that, I wanted to highlight one very important point. That is, in a boost converter, the choice of the L, which comes from the choice of the delta IL. So the choice of L does not significantly affect the capacitor selection, unlike in a boost converter. Unlike in a buck converter. In a buck, we saw that it is really the product of L and C that affects the output voltage ripple, and therefore the C was roughly inversely proportional to the L value that we select. So if we chose high value of L, then we could use a smaller capacitor in a buck converter. But in a boost, for a given output voltage ripple specification, there is not such a strong correlation between the L and C. So it's kind of independent in the case of a boost converter. Now coming back to what value of D should we substitute in this expression for the L, we should really design for the worst case condition. That is to say that no matter what is the operating condition, L should be chosen such that delta IL is no more than the value that we chose. So again, looking at this expression, VO, TS and delta IL are constants for a given application and for a given choice of delta IL. Therefore, the variable term is the D times 1 minus D, and we should maximize this term such that the value of L that we chose is guaranteed to limit delta IL to be less than or equal to the value that we chose for any value of D. Now, if you look at the plot of delta IL versus D, we see that for both D equals 0 and D equals 1, delta IL is exactly equal to 0, and the maximum value of delta IL is obtained when D equals 0.5. So when D is 0.5, D times 1 minus D is 0.25 or 1/4. That's what gives this expression for the maximum value of delta IL. So we should substitute D equals 0.5 in this expression as the worst case condition. Now we can get the same result analytically by taking the derivative of this expression, that is dl over dd, and equating that to 0. So the derivative here is the constants VO, TS and delta L are shown here, and the derivative of d times 1 minus d is 1 minus 2d, and equating this to 0, we get 1 minus 2d is 0, or d equals 0.5. Same result as we got from the plot. So we should substitute d equals 0.5 for the worst case condition, but if the operating range does not include d equals 0.5, let's say our operating d is only between, say, d equals 0.2 here to, say, d equals 0.4, so 0.2 and 0.4, d equals 0.4, then we should pick the value of d that is closest to 0.5. That is what gives you the maximum value of delta IL, and that ensures worst case design. Okay, in this slide, I summarize all the requirements for the input inductor. So we already established that the required value of L, or the inductance, is given by this expression, and in this we should substitute d equals 0.5. If d equals 0.5 is not within the operating range of d, then we should use a value that is closest to 0.5. Now the other parameters required for selecting L include the peak inductor current value, and that is equal to the maximum input current average value plus 1/2 of the peak to peak ripple that we chose. Next, we also need the DC bias in the inductor current, and that again is equal to the maximum value of the average input current. and we may also express that in terms of the load current. So in that case it is I0 max over 1 minus D, and here we should use the D max value to get the maximum DC bias in the inductor current. And finally, the RMS current is an important parameter to design the wire gauge for the inductor windings, and that is given by this expression. So if the delta IL is small enough, then the IL RMS can approximated to be just IN max, assuming delta IL to be very small. The IL RMS itself was derived by considering the average IN first, so that's IN squared, and then the switching frequency ripple component separately. So that is the triangular wave shape with its mean squared value being delta IL squared over 2 square root 3 whole squared, which is 12. Next we will look at the selection of the output filter capacitor. In a buck converter, we saw that the output capacitor is selected based mainly on its ESR requirement. However, in a boost converter, the capacitor selection is really dictated by the RMS current requirement. So that is because in a boost converter, the RMS value of the current through the capacitor can be really large. It can even be higher than the maximum load current value itself, as compared to the buck converter, where the RMS current in the output filter capacitor was only about 5% of the load current. So in a boost, it's really the RMS current requirement that decides the selection of the capacitor. So let's derive the RMS value of the capacitor current, and here is the capacitor current waveform, and during the on interval its value is negative I/O. It is supporting the complete load current, and during the off interval the IC is IL minus I/O. So this is really IL minus I/O. That is this red waveform, and we are going to approximate this at least initially by a pure square wave current, and in the on interval it's exactly the same as the complete current wave shape, and during the off interval it is approximated by the straight line of value equal to the average of IL, which is IN, minus the same load current IO. Now if you look at the RMS value of this just a square wave current, then this is obtained by taking the square of the instantaneous values. So during the on interval it is IO squared for a duration of dts, and the ts gets cancelled, and during the off interval the magnitude is IN minus IO, square that multiplied by 1 minus D, and that gives you the mean square. Take the square root of this entire all the entries, we get the root mean square, or the RMS value. Now we can get the expression for the IC RMS completely in terms of the load current IO and the duty ratio D. In order to do that, let's substitute for IN the expression in terms of IO, which is IO over 1 minus D, which comes from power balance. So if you substitute IN in this expression, what we get after just 2 steps is that IC RMS is equal to the load current IO times square root of D over 1 minus D. So clearly for D greater than 0.5, we see that the IC RMS is even larger than the load current itself. So that's a large current through the capacitor, and that is why the capacitor selection is completely dominated by the RMS current requirement. And obviously in this expression we need to substitute the IO max value if the load current is changing, and for the D we should use T max. That is what maximizes this expression. Now this is an approximate expression for the RMS value. If you want the accurate value for IC RMS, all we need to do is just retain what we calculated for the square wave current, retain its mean square value, and then consider the mean square value of just the ripple component, and then add the 2 and take the square root of that to get the complete IC RMS. The result would be shown here, and so in this, if delta I is 0, then we get back our original expression. Now, to see how good an approximation this square wave way of calculating RMS is, let's look at the plot of this complete expression versus this approximate expression for different values of delta I. So consider delta I to be 0, which is the original derivation, and then 20% of the average inductor current, and another case where delta I is 50% of the average inductor current. And what is plotted is the IC RMS as a ratio of the load current versus the duty ratio D, going from almost 0 up to about 0.7. You can clearly see that there is almost negligible difference between the approximation and the actual value of ICRMS, especially for D greater than about 0.3. They actually merge on top of each other. So what is shown here is a very good approximation for the RMS current value, and we can use this for deciding the capacitor. This plot also confirms that for D greater than 0.5, which is summed here, we see that any D above 0.5 results in the ICRMS being higher than IO itself. So anywhere beyond this, the ICRMS is higher than IO. In this slide, we will summarize all the parameters needed for the correct choice of output capacitor. So we already established that the C selection is going to be based on the RMS current requirement and the values that need to be substituted in the expression that we derived in the previous slide, or the maximum load current and the maximum value of the duty ratio. Now, if we choose the C based on the RMS current requirement, it is most likely that we will meet the delta VO specification as well, which is the important specification to be met, and this is decided by the C value and the ESR value. So the method is to design based on the RMS current, but do check for delta VO for the obtained value of C and the ESR. So the expression for delta VO in terms of just considering the ideal capacitor just due to the capacitive impedance, so C dV over dt is IC, and considering, for example, the on interval, the dV by definition is delta VO, and IC in this interval is IO, at least the magnitude is the load current IO, times the duration, which is dTs, over the capacitance, that is delta VO. Now, once you've chosen the capacitor based on the RMS current requirement, substitute the obtained value of C in this expression and check for delta VO. Now, the delta VO should be much less than what is the specification for delta VO. The reason for it being much less is because the ESR ripple component is the more dominant ripple component. Therefore, we need to make the capacitive impedance component of the ripple negligible. Then the expression for the ESR limit, this would be the complete delta VO, assuming that the entire ripple is due to the ESR. So the specified delta VO divided by the peak-to-peak variation in the capacitor current. Now the peak-to-peak variation occurs during this step. So essentially this point is IL minus IO. So the difference is really just IL peak. So it's the ESR should be less than delta VO divided by IL peak or IN peak. And finally, the voltage rating should be the maximum output voltage VO. So essentially, we need to meet 4 requirements for the capacitor selection: the voltage rating, the RMS current rating, and the C and the ESR values as given by this expression. Okay, so finally we come to the switch ratings, the ratings for the MOSFET as well as the diode. Considering the MOSFET, The voltage rating, that is the voltage across the switch when it is off. So when the switch is off, the diode is conducting, and this end is now physically connected to the output voltage. Therefore, the maximum voltage that the switch sees, neglecting all non-idealities, is the maximum output voltage VO. So that is the voltage rating. This plus sufficient safety margin. Now the peak current is the peak inductor current, and the peak inductor current is the IN, maximum value of IN under all operating conditions, plus 1/2 of the peak-to-peak ripple that we allow in the inductor current. Now for a MOSFET, the RMS current is also an important parameter. So the switch RMS current, if you look at the switch current, it conducts IN max for a duration of DTS and 0 current during the 1 minus D period. Therefore, the RMS value is simply the IN max times square root of D. And if you want to express this in terms of the load current, then this would be IN max is IO max over 1 minus D. That times square root of D is the required RMS switch RMS current rating. Looking at the diode, it has the same voltage rating. So when the diode is off, the switch is conducting, this end is grounded, therefore the voltage across the diode is VO. The peak current rating is exactly the same as that of the MOSFET. Both are the inductor current peak values. For a diode, it is the average current rating which is more important, and just by looking at the circuit, we can see that since the average current through the capacitor is 0, the average diode current is exactly same as the load current. So we should consider the maximum load current, and that is the average current rating for the diode.